Okay, we've got about 30 slides left. Let's try and do them all in one, maybe 30-minute or so chunk, and then we'll be done with lectures for fall of 2017. All right, the last set of 30 slides is what I'm calling here classic speech perception experiments. So, why do we care about speech perception? Well, cognitively, it's an interesting task, right? So, in the context of a liberal arts undergraduate major, it's a really interesting example of human behavior that draws on a lot of different skills. But for a group of people who aspire to be speech-language pathologists and audiologists, we care about it because problems with speech perception are associated with a lot of different communication disorders. And the most obvious one is hearing impairment. So one of the biggest complaints of people with hearing impairment is that they have trouble understanding speech. Maybe it's a little bit less intuitive, but true nonetheless, that there are lots of other developmental speech problems that are associated with subtle deficits in speech perception. So even for kids with normal hearing, problems with speech perception of the type we're going to talk about with the remaining 30 slides are associated with things like dyslexia, language impairment in preschool children, so having a delayed onset of language, problems learning words, simpler syntax, etc., and pronunciation problems in kids. So kids who have extremely inaccurate pronunciation, well beyond the age after which speech errors should end, those kids have subtle deficits in speech perception. And a lot of what we know or think we know about speech perception in individuals with communication impairments comes from speech perception experiments that use a very constrained and a very special set of methods. And I don't think they're the best methods, quite frankly. In fact, I would be a lot happier if we kind of started over from scratch with thinking about speech perception and its relationship to communication disorders, but that's just not the way science works. You know, science inherits a set of findings from the previous generation and kind of works with it. And a lot of what we think we know are based on experiments that were done for very specific reasons with very specific stimuli. And in our remaining 30 slides, you're going to get, with plenty of shade thrown, an overview of speech perception in the sort of classic mold. And we'll start out thinking about what people in speech perception, classic speech perception research, use as stimuli. So in the past, really month or so, we've been talking about the perception of talker attributes using natural recorded productions by actual human beings, right? So we've used what we call recorded natural speech. That's number 2 here. Sometimes it's been edited. So there was at least one example I gave you of a study that Sarah Mack and I did where we took natural productions of words that began with S and we took the natural S's off and replaced them with other S's. That's edited natural speech. Sometimes we didn't really talk about things presented in noise, but you heard things in noise in your homework assignment, right? Now that's very different from the kind of stimuli that are used in speech perception experiments in the classic mold, which have used synthetic speech. So let's talk a little bit about speech synthesis. Speech synthesis is intended to mimic the patterns of natural speech tokens. The original synthesizer was developed at a place called Haskins Laboratories, which is a sort of semi-autonomous laboratory that's affiliated loosely with Yale University. So it's in New Haven, Connecticut. I don't really understand its organizational structure. I know that it's a standalone, it's like a floor of an office building in New Haven, but everybody I know who works there has an affiliation with either Yale or with some other university in that area, University of Connecticut, some of the New York City universities. And Haskins was really influential in a lot of early speech research, along with AT&T Bell Labs, which was sort of on the other side of New York City in Murray Hill, New Jersey. But Haskins sort of made its fame, sort of initiated its fame by developing a speech synthesis system called the pattern playback. The way the pattern playback system worked is very interesting. I will post a link to a history of speech synthesis from the Haskins website. I mean, literally people painted schematic spectrograms on glass and then somehow through engineering that, is beyond what I can do, they were able to take those physically painted schematic spectrograms, things that look like what you guys have been making on your exams and on the whiteboard in class, they turned those into synthetic speech. Very interesting. But speech synthesis got better and better over the years, and essentially what the way speech synthesis works is the following. Depending on what the target speech segments are, you select values for a wide range of parameters. For example, you can choose what the form and frequencies are, and you can make changes in form and frequency over time. So you could synthesize a vowel that was just a steady state ah by choosing F1, F2, F3, etc. values, or you could make ba by changing the formants so that you had the formant transitions that were appropriate for an initial bilabial. You can also make things that aren't vowels, so you can make little bits of aperiodic is the word I couldn't think of, little bits of aperiodic noise that mimic stop bursts and frication intervals. And you can choose lots of other parameters too. Now, the CLAT synthesizer, I guess I overly edited this, so we missed a page called the CLAT synthesizer. So the pattern playback was the first system, and then starting in the 70s, a person named Dennis Klatt, who unfortunately passed away quite early in life and is no longer with us, Dennis Klatt made a synthesizer which just goes by the name the CLAT synthesizer. And it's the one that was described on the previous slide, where you're not painting things on glass, you're actually programming them in line by line. But the CLAT synthesizer isn't the only game in town these days, and in fact, all the big computer companies want to make their own speech synthesizers. And in fact, at Haskins Labs itself, speech synthesis has taken a new direction in the last 20 or so years, where they've been building synthesizers that are based on articulation. And remember the unfortunately named pink trombone, which is still on your Moodle page, that's an articulatory synthesizer. So that's a synthesizer that doesn't ask you to program in different form and frequencies. It's a synthesizer that says, look, tell me what kind of a vocal track you want, and I will use my knowledge, so I'm speaking as if the articulatory synthesizer were a human, I will use my knowledge to synthesize a sound based on vocal tract acoustics. And that's another thing that Haskins has developed that's becoming wider and more widely used. So articulatory synthesizers compute lengths and areas of vocal tracts and produce speech sounds accordingly. And can also synthesize vowels and consonants, as you guys saw, and can continue to see if you go back and play with that. This is iced coffee, by the way, not flat Pepsi. I don't know why it's important to me that you know that. Pepsi. Why would you think Pepsi? All right, speech perception experiments are not the only use for synthetic speech. So there's a use for speech synthesis in things like augmentative communication devices. So some augmentative communication devices, like the one used by Stephen Hawking, use synthetic speech. There are toys, video games, automatic communication systems like the communication systems you call into sometimes for travel reservations, etc., that use synthetic speech. Why synthetic speech? Why not just edited natural speech? Well, the problem is this. Think about something like a sequence like pa. The stop in pa in natural speech has a lot of different components, each of which are potentially very important for telling you that this is a P in pa and not a T in ta, or a P in pa instead of an F in fa. So in pa, that stop has a burst with a spectrum that is distinctive given that bilabial place of articulation. So it has the concentration of energy in the lower frequencies. It also is associated with formant transitions for the following vowel. And it has its own voice onset time, which tells you that it's pa and not ba. Right? So straight away, we see that the P in pa has at least three things that are uniquely associated with it. Its voice onset time, its formant transitions, and its burst. So, which of those three things is the sort of critical minimum bit of information that you need to perceive that P in pa? If we wanted to look at that, we would have a really hard time with natural speech producing, say, a burst for pa, but formant transitions that were appropriate for ka, right? We just don't have that ability as human beings to make that kind of an articulatory maneuver. Because in natural speech, all of those parameters vary at the same time. Going too fast here. But with speech synthesis, one can make, and I don't know why that's in scare quotes, one can, let's say, synthesize, or one can construct. Now one can construct a stop vowel syllable with a particular set of desired attributes. So you can synthesize the stop with a burst or without a burst. You can vary the value of the voice onset time. You can vary the frequency and the duration of the formant transitions. And by synthesizing speech and manipulating those different parameters separately, you can observe what are the minimum cues needed to recognize a particular speech sound or tell it apart from another speech sound. That's what I mean when I say discriminate speech sounds. The typical modus operandi for these classic speech perception experiments that I'm telling you about are to, first of all, hypothesize that a particular acoustic parameter is crucial for the perception of a sound. So let's hypothesize that the shape of the spectrum for the burst in pa is critical to perceiving it as pa and not as ta or da. I'm sorry, not as ta or ka. Next thing you want to do is synthesize a continuum that varies in that parameter. So with speech synthesis, we can create a set of stop bursts that go from the in pa at one end to the in ka at the other end. And we can come up with, 10 different intermediate forms between pa and ka. So if we have the shape of pa as one of our endpoints and the shape of ka as the other endpoint, we can synthesize bursts that have every interpolation between them. So if this is your, shape of the burst for pa and this is the shape of the burst for ka, you can synthesize this burst and this burst and this burst and this burst and this burst. So I hope that came out on the camera and wasn't off camera, but I can't see myself as I'm saying this. Point being that you can synthesize differences in the burst shape and ask people, was this pa or was this ka? So you can do what we call a two alternative forced choice test. You give people two alternatives, was it pa or ka? And you force them to choose between them. You don't let them pick a third other option. Then you can collect a bunch of responses. Play these stimuli to listeners with the different bursts. Play each stimulus multiple times so that you can look at people's consistency in responding. Play them to multiple people so that you can make sure that this isn't just something that's quirky and associated with only one person. And see whether or not their perception of these sounds changes as a function of the burst shape. So we could synthesize a sa and a sha, and look at what we've got here. We've got a sa that has a particular interval of frication, but also has a particular F2 frequency. Sha has a different interval of frication and a different F2 frequency. So we can synthesize a continuum that varies either the frication or the F2 frequency, or maybe both, and ask people in a two alternative forced choice task, is this sa or sha, and see whether or not their perception changes. So if we look at the sa and sha spectrograms on the previous slide, we could hypothesize a number of different parameters that might differentiate between those sounds, like the frication spectrum or the F2 frequency. Okay, now let's imagine we did that experiment where we synthesized the burst shape differences between pa and ka. And we found that when you changed the shape of the burst, you changed people's perception and it went from pa to ka. Well, what we would be observing there is a change in speech perception that was caused by a change in some acoustic aspect of the signal. Now, what we would call this then an acoustic cue. We would say that the shape of the burst spectrum is a cue to the difference between pa and ka, a cue to the place of articulation of voiceless stops. So we say something is an acoustic cue when changing it changes perception. Now, this term here is why I'm bothering to present this rather archaic way of thinking about speech perception, because acoustic cues are hugely influential in particularly things like hearing impairment research. So in the early days of speech perception research, people basically cataloged the acoustic cues for sounds. So they cataloged what are the cues for place of articulation for voiceless stops, what are the cues for place of articulation for fricatives, what are the cues for the perception of vowel height and backness. And they came up with a list of the cues. And those cues are essentially what people then in the development of prostheses decided were important. Now, what do I mean by prostheses? Well, when I say hearing prostheses, I used to mean hearing aids. So people really cared about acoustic cues in the development of hearing aids because they wanted hearing aids to amplify the things that were most important for the perception of speech sounds. And acoustic cues were what people, they were people's first guess at what the most important speech attributes were. Nowadays, prostheses include not just hearing aids, but also cochlear implants. And cochlear implants are very much, the design of cochlear implants was very much influenced by what people think the acoustic cues for speech sounds are. So cochlear implants sort of selectively encode acoustic cues and stimulate the auditory nerve to give you the perception of those acoustic cues. So the lives of people with hearing impairment who use cochlear implants or hearing aids have very much been influenced by what we're learning here. The fact that just a couple of, a dozen or so slides ago I said I think we really need to rethink this from scratch is motivated in part by the fact that hearing aids and cochlear implants are quite good. Really quite amazing if you think about it, but they're far from perfect. And so one wonders whether or not we need to kind of rethink from the ground up whether we've been doing the right thing in our search for acoustic cues. End of editorial. So acoustic cues can be varied in small steps. And this set of stimuli that vary in those small steps is called a continuum. One of the few words in English that has UU together. So we could make a continuum in voice onset time by varying voice onset time in small steps. So we could start out making a ba with 100 milliseconds of voicing lead, a negative 100 milliseconds voice onset time. And then synthesize that all the way up to pa with 100 milliseconds of voicing lag, so a plus 100 milliseconds voice onset time. And we could see which one, we could make many stimuli, good 2021 stimuli here that varied in voice onset time in 10 millisecond steps, and ask people, we could synthesize, say, all the way from ba to pa with 10 millisecond steps, and ask people to tell us, was this pa or ba? And what we would be able to find out, if we pooled our responses, if we averaged responses across listeners and across multiple repetitions of each stimulus, what we would find is essentially what is the length of voice onset time that we need to be able to say that a sound is no longer ba and is pa. We could do the same thing by changing the F2 transition in small steps, or by changing the length of F1 and F2 transitions. We can, with speech synthesis, we can vary anything. And this is what people did back in the 60s, starting back in the 60s when they began this endeavor that I just talked to you about of cataloging acoustic cues. People began to study the people's perception of formant transition continua. Continuum is a Latin singular, continua is its plural. And that's one of those Latin plurals that I can't not say. So I can't say continuums. I can say symposiums, but I can't say continuums. I have to say continua. So Lieberman, Cooper, Shankweiler, and Stoddard-Kennedy studied a continuum of vowels all beginning with the consonant D. So what they synthesized, this was using the pattern playback. So this is where they painted those form and frequencies, and then through something akin to magic, they got synthesized speech tokens. What they found is that you could synthesize formant transitions for a variety of vowels, and when you played these to listeners, even though there was no burst in these stimuli, remember stop consonants have bursts, even though there was no burst in these stimuli, simply hearing the formant transitions was enough to tell people that there should have been a consonant D there. So that was one of the first illustrations of synthetic speech used to study speech cues. Now that very same research group got into an endeavor, a sort of, we call it a cottage industry, sort of a set of studies that they were doing over and over again that showed the following. What they showed is that if you make a continuum of sounds and give people a two alternative forced choice task, people's perception as you go from one end of that continuum to another seems to jump from the perception of one sound to the perception of another. So I got ahead of my text. Changes in perception seem to jump from one phonetic category to another with small acoustic steps. And the classic speech perception experiments had two parts. They had identification tasks where people were playing stimuli and asking listeners, is it A or B? Is it da or ta? Is it ba or da? So those are identification tasks, and they were often given with two alternative forced choice response sets. So you were asked, is it one thing or the other, and you couldn't say neither or both. Another part of these experiments is what are called discrimination tasks, where you played pairs of stimuli, usually adjacent pairs on that continuum. So if the continuum goes from -100 to +100 in 10 millisecond steps, your identification task would be to hear the -100 stimulus and tell me, is it ba or pa? Your discrimination task would be to hear the -100 followed by the -90 and then being asked to say, were those the same or different? And what speech perception experiments show, this is kind of fun, well, not fun in the capital F sense. All right, not fun in the truly fun sense. Identification experiments, so just to put text to what I said, listeners have to label stimuli, and it's typically done with a small set of responses, often just two, and you're forced to choose among those responses. You don't get to say other. So in a voicing study, you might be asked to label stimuli as either the voiced variant B or the voiceless variant P. In a place of articulation study, you might be asked to label stimuli as B or D or G. In the discrimination task, you're played two stimuli and asked are they the same or different. And you might use what's called an AX procedure, where you are trained to listen to a standard sound and then you're played a single stimulus and asked was it different from that standard or not. You might use an ABX procedure where you're asked to say whether or not two sounds are different from one another. Now, what the identification experiment showed, and this is where another one of the things that classic findings in speech perception that I feel obliged to teach you, is that when you do experiments like this, you get very often the same result over and over again. And that is that your identification results show that listeners sometimes label stimuli into categories, and these categories have sharp boundaries. What do I mean? Well, it's best seen on a figure. So this is a figure that's showing people's perception of a voice onset time continuum. So on the x-axis here, you have milliseconds of voice onset time, going from -73 to +77 in, I don't know what this ends up being, if it ends up being the same number of milliseconds from step to step, but it should be around 12 to 13 milliseconds step to step. It doesn't look like it's equivalent across this, but whatever. I'm pretty sure these are fake data anyway. So what this is showing is in the blocks, it's showing the percentage of time that people identified the stimuli as T. In the filled squares, it's showing the percentage of time that people identified it as D. And in this hypothetical experiment, we would have had a two alternative forced choice, meaning people would have been asked, is it T or is it D? And you had to say one or the other. So the filled blocks and the open blocks are going to add up to 100 in every case because those are the only two options. And what you see here is what you see over and over and over again in speech perception experiments, and that is that there is a big range for an acoustic parameter where you're always identifying the sounds the same way. Okay, so whether or not the voice onset time is minus 61 or minus 24, you're always identifying it as D 100% of the time and T 0% of the time. So it's not like going from this voice onset time to this voice onset time makes something sound slightly more T-like. It's not until you get to between 0 and 22 that anything changes. There's one stimulus here for which it's 10% of the time labeled as T and 90% of the time labeled as D, but that's the only stimulus that isn't responded to consistently. Now, this has been influential for, this is where I think we need to go back to the drawing board. What people argued for ages and ages and ages is that this finding means that people can't hear differences in this range. That people are simply deaf, so to speak, so let's put deaf in scare quotes. People are deaf to the difference between minus 61 and minus 24 milliseconds voice onset time. And in fact, discrimination tasks bear this out too. So if you play these two stimuli and ask people are they the same or different, people are generally going to say most of the time, if not all of the time, same, right? So even though they're different stimuli in their voice onset time, people, if they label them the same, will say that they are the same in the discrimination test. Whereas if we look at the difference, if we played the stimulus with 0 milliseconds voice onset time and 22 milliseconds voice onset time and asked people same or different, people are going to say different. Because 0 milliseconds voice onset time is identified as T 0% of the time, but 22 milliseconds voice onset time is identified as T 100% of the time. Now, that's all well and good, right? I'm not disputing these findings. What I'm saying is that for years and years and years, people said, well, then it really doesn't matter what the voice onset time is down here. People can't hear it. So we only want to develop our auditory prostheses, our hearing aids, our cochlear implants to amplify and code the things that are in the critical regions, right? But as it happens, people can hear these differences rather easily, and one of the ways that we know this is that when you vary stimuli along voice onset time and ask people to rate something about the talker that is related to voice onset time. So let's say that voice onset time is important in the identification of African American English versus other varieties of English. And it very well may be. There's some emerging evidence even presented at the conference I'm at right now that this is the case, right? Well, if you ask people to make inferences about whether the speaker is an AAE speaker or not, if this is important for AAE, people are going to label speakers differently depending on whether they have heavily pre-voice stops or not, right? It's only in the context of these two alternative forced choice tasks and these two alternative discrimination tasks, same or different, that you get this pattern. And we call this pattern categorical perception. Categorical perception is the phenomenon in which small changes within a category result in the same perception, the same identification, and judgments of same when you're asked to discriminate. But once you vary things across a category boundary, so here we've got the category boundary where the T line and the D line cross one another. Once you vary things across a category boundary, suddenly perception is much better. So discrimination results show poor performance, poor ability to discriminate pairs of stimuli within a phonetic category, but good performance across a phonetic category boundary. So these experiments show that listeners are able to put acoustic events into speech sound categories, to say a sound is either P or B. And that they can discriminate between speech sounds. They can discriminate sounds that are on different sides of that boundary. Right? Now, the problem with categorical perception isn't, like I said, anything in the soundness of the methods. It's in sort of over-interpreting the results, right? How often in life do we make two alternative forced choice judgments, right? We actually have lots of uncertainty about speech perception from day to day, right? We make more graded judgments. And when I say graded judgments, I mean like, we don't say this word is sack or shack. We say, I'm very certain that it's sack, or it might have been shack, something like that. So this is categorical perception has probably, I mean, it was a very influential finding, and it got speech perception research off the ground and got us thinking about things. But people have made, I think, far too much about individuals' inability to perceive things within a phonetic category. All of the stuff that we talked about with perceiving speaker attributes for the last month, that's all been stuff showing that actually people perceive stuff within phonetic categories really well when we ask them to use that information to identify things about a speaker, their age, their sex, social class, stuff like that. Okay, so that was an editorial. And let's end on this slide and say that there's another problem with this stuff on phonetic perception of synthetic speech, and that is that think about the stuff we've talked about in class. Think about the stuff we talked about with perceiving whether or not someone is an orthodontist or whatever the example was, a dentist, right? People want to be right in experiments. So let's imagine we made 3 S to Esh continua, one of which varied in the spectrum of the frication noise, one that varied in the formant transitions, and one that varied something else. So we could easily make a fricative with an ambiguous spectrum and ambiguous formant transitions, but we could vary the loudness of the frication interval itself. If we did perception experiments where we looked at the perception of these 3 continua, all of them would elicit a change in perception from S to Esh, right? So what happens over the course of these perception experiments is that people learn that in this experiment, it is my job to assign whatever is varying in the continuum to whatever categories you've given me, right? People perceptually learn what they're supposed to do, and nobody wants to be wrong. They do it. They do it to the best of their abilities. So you learn that, maybe relative amplitude, that loudness of the fricative compared to the following vowel, maybe that's a really weak cue to ask the S-Esh difference to you. But if you're put in a sound booth and you're given a stimulus continuum that only varies in relative amplitude, and you're asked, is it S or is it Esh, you're going to do the right thing. Which when I say do the right thing, I'm using that because it's the title of one of the best movies ever made. But you're going to do what human beings do, which is, you're going to comply, right? I mean, you're going to be a good citizen and figure out, what's the answer to this, right? You're going to figure out the crossword puzzle answer on whatever information you have, so to speak. And the problem here is that we've done this a lot in the last 50 years. And as a result, what we found isn't so much things about what we use to perceive speech, so much as we found that human beings are really good at using minimal information to identify speech when they're put into a context in which they're forced to do so, like a speech perception experiment. So as you move forward, particularly those of you in audiology and as many of you go into hearing science, just keep in mind that this is what a lot of speech perception research is based on, the continua that I've been telling you. And I've published on it, right? So Dr. Nelson and I have an article that gets a healthy number of citations that looked at the perception of synthetic speech continua in adults with cochlear implants and normal hearing adults. It's not like I'm trashing it entirely. It's not like I'm saying that this is completely debunked in the way that something like facilitated communication has been completely debunked. And if you don't know what facilitated communication is, look it up. It's really interesting. And it's pseudoscience. This isn't pseudoscience. It's just, it's taken us down a garden path. And I think moving forward, we can do a little bit better. Okay, see you Tuesday, and thanks for being flexible with me this week and being willing to watch these videos over the web in lieu of going to class. And I'm really sorry about how icy it is there. It was really tragic for me to have to be in 85-degree weather yesterday. Okay, now you all hate me even more. Bye-bye.